Today we are going to discuss about the solar cell experiment. The major aim of this experiment is to draw the current voltage characteristic of the solar cell and to find out its efficiency and the fill factor. So before going to the experiment part, let us have a glance what is the significance of doing this experiment and where it is being used. So to understand that, let us look at the current energy sector in India. We know that the energy sector plays a very vital role in the growth of the country's economy. So this pie chart shows the source-wise installed power generation capacity by 2019. And we can see that the thermal energy contributes around 63% of the total generation capacity. And the renewable energy includes around 23%. 12% is for the hydropower and 2% is for the nuclear power. So the renewable sector is placed at the second place after the thermal energy. And what is this renewable energy sources? So they are the wind power, the solar power, the small hydropower, biopower, waste to energy, etc. And what is the need of using these renewable energy sources? Because the non-renewable sources like the thermal and the nuclear energy sources, they are having the detrimental effects on the environment. So there is a definite need to go for the renewable energy sources. So as per the 31st December 2019 data, we can see that the highest participation for the renewable energy sources is wind power, which contributes more than 40%. Whereas the solar power contributes around 40% to the renewable energy resources. And it is a great pleasure to see that India has witnessed around 13-fold increase in its solar generation capacity from 2.6 gigawatt in 2014 to around 33 gigawatt in December 2019. In fact, the International Renewable Energy Agency has estimated the global solar installation that it will reach around 2.9 terawatt by 2030. In 2018, this number was 480 gigawatt. And what is the material that is mostly used for the solar cell panels? It is the silicon. Here is the picture of the silicon ingots and the silicon wafers. And what is the cost of the solar cell or the solar panel? So the solar power cost in India is around 2.5 rupee per unit as per the 2019 data, whereas it was around 17 rupees per unit in 2010. So we can see a drastic reduction in the solar power cost in the country. So this is a brief significance of the experiment. So the next part will be discussing physics behind the solar cell. So the solar cell is basically a PN junction under the light illumination. So what happens to a PN junction when we illuminate the light on it? So first of all, the electrons and hole pairs, they are generated, and that is called as the photon generation. The photon generation process takes place in the light absorbing material. In most of the conventional solar cells, the light absorbing material is silicon. And the second step is to effectively separate the electron hole pairs. And the effective separation of the electron hole pairs lead to higher efficiency of the solar cell. So these are the two basic processes. One is the photon generation and second one is the separation of the charge carriers. So now let us have a look at the band diagram of the PN junction and what happens to the PN junction when we shine light on it. So this is the conduction band and the valence band of the p-side semiconductor, and this is the valence band and the conduction band of the n-type semiconductor. And we can see the Fermi level is equilibrating across the junction. So when we shine a light having energy more than the band gap of the material, what happens is that the electrons and the holes are generated. And these solid circles are the electrons, these empty circles are the holes. And since there is a built-in potential across the junction, the electrons, they flow towards the n-type semiconductor and the holes, they climb towards the p-side semiconductor. As a result, there is a current flow from n side to p side. So this leads to the generation of a potential, and the p-n junction becomes forward biased. Up to what distance the electron and hole they are significant? The distance is up to Ln and Lp, which are called as the diffusion length of the electrons and the holes. After this distance, the electrons and the holes, they recombine, and we cannot collect them across the contacts at the p terminal and the n terminal. So the total width that is of our significance is Ln plus W plus Lp, where W is the depletion width. Ln and Lp are the corresponding diffusion length. So as a result, now there are two kinds of current. One is the light generated current, which is independent of the potential that is generated across the junction, and another one is the dark current, which is due to the diffusion of the electrons and the holes. So when light is illuminated, we are having these two currents, and when we add these two currents, we can get this corresponding curve. And the total current is the combination of the Shockley diode current and the light generated current. So the convention is to plot the current as positive, because we are going to generate the power. So we will get a inverted current voltage graph. So now let us have a look at the model graph and the formula that is required for the particular experiment. So now let us have a look at the model graph and the formula that is required for doing this experiment. So this is the model current versus voltage graph, and together with that we have plotted the power as a function of the voltage. Here there are three important points. One is the short circuit current, for which the corresponding voltage is 0, open circuit voltage, for which the corresponding current is 0. And the VOC and ISC are the maximum voltage and the maximum current that can be generated by the solar cell. Together with that, we have plotted the power as a function of the voltage, and this point corresponds to the maximum power, and correspondingly VMP and IMP are the respective voltage and the current. Ideally, the current voltage graph should be a perfect square, but due to some parasitic resistance, it doesn't take the shape of a perfect square. So how much this graph attains the squaredness is called as the fill factor. So the fill factor can be defined as the ratio between the product of VMP IMP and VOC ISC. Ideally, this fill factor should have been 100%, but due to the leakage current, it is not completely 100%. Rather, it is less than 50, 60 or 70%. So more is the fill factor, better is the solar cell. So now let us define the efficiency of the solar cell. So the efficiency of the solar cell is defined as the ratio between the output power to the input power. And what is the output power here? Output power is the product of the voltage corresponding to the maximum power and the current corresponding to the maximum power. And AC times omega correspond to the input power, where AC is the area of the solar cell and omega is the incident intensity. And the incident intensity can be changed by changing the distance of the light source. So using these two formulae, we are going to find out the fill factor and the efficiency of the solar cell. So now let us go to the experimental setup and try to take some readings for this current voltage graph, and then we'll come back and plot it. Then we'll finally obtain the efficiency and the fill factor of the solar cell. So now let us come to the experimental part. So first of all, here you can see the light source that you are using for the solar cell experiment. Since we are not using the natural sunlight for doing this experiment, we are going to use one light bulb. Inside this there is a light bulb which we are going to use as the source of light. And next to it we are having the solar cell here. This is the solar cell. So light is going to incident on the solar cell perpendicularly. So, and we are going to adjust the distance between the source of light and the solar cell. So let us adjust the distance. So currently the distance is, so this is the scale, ordinary scale. So using this we can measure the distance between the surface of the bulb to that of the cell. So currently we can see that the distance is around, distance is 13 centimeter. So as the distance between the cell and the light source is going to be changed, accordingly the intensity is going to be changed. So here in this panel we can see according to the distance the intensity of light is different. So currently the distance between the source and the panel is 13 centimeter. So the corresponding intensity, it is 77 watt per meter square. So accordingly for all the distances the intensity has been pre-recorded. So now we can see these terminals of the solar cell panel are connected to this circuit. So this circuit contains a voltmeter and an emitter across a load resistance. The voltmeter conventionally it is connected across in a parallel way, and the emitter is connected in series. So now let us start doing the experiment. So let me switch on the light source. So now we have switched on the light. So the light of 77 watt per meter square now is falling on the solar cell. So we can see here there is a load resistance connected across the two terminals of the solar cell. So the load resistance, we can see there are different values mentioned here, 10 ohm, 22 ohm, 33 ohm, 47 ohm, like that up to 470 ohm. And at the end here there is a SC, it is written. SC means it is the short circuit. That means a very low resistance is connected across the two terminals. So first let us take the readings, that is the open circuit voltage and the short circuit current. So open circuit means we have to connect nothing in between these two terminals of the solar cell. So that means let us open the circuit here, and we have to measure the corresponding voltage. We have to note down the corresponding voltage. The current as such, it is 0, as we have seen that in the IV characteristic, the model graph, the current corresponding to open circuit voltage is 0, and we can note down the corresponding reading for the open circuit voltage, which comes out to be, here we can see the scale is from 0 to 2 volt. So we can see between 0 to 0.5 there are 10 readings. So this is 1.5, this is 1.75, then 1.80, 1.85, and this is 1.90. So we can record the corresponding VOC to be 1.90 volt, and as such the corresponding current is 0. So now let us look at the short circuit current. For that we have to reconnect the load resistance, and we have to put this knob at the short circuit point. So here, this is the knob here, this is at the short circuit point, and here we can see that the voltage is 0 and the current is having some value. So now let us note down the value for the current. So between 10 and 20 we have to note down the reading. So this is 15, this is 12, 14, this is 16. So this is the 16 milliampere. So the current that is noted is 16 milliampere, which correspond to the short circuit current. So now we are having two readings. One is the open circuit voltage, which is 1.90 volt, and other one is the short circuit current, which is 16 milliampere. So now in between we are going to change the load resistance. So let us put it at 10 ohm, and again we have to measure the corresponding voltage and the current. So now we can see the voltage is, it is between 0 to 0.25. So this is 0.05, 0.1, 0.15, and this is 0.2. So the corresponding voltage is 0.2 volt or 200 millivolt, and the corresponding current let us measure. So this is 12, 14, and this is 15. So the corresponding current is 15 milliampere. Again, we can change the load resistance to 22 ohm. 22 ohm, and now we can see that the corresponding voltage is 0.5 volt, and the corresponding current remains fixed at 15 milliampere. So like that, we have to note down the readings for all the voltage and the current by changing the corresponding load resistance from 10 ohm, 22 ohm, like that up to 470 ohms. And then we have to plot the graph and obtain the corresponding efficiency and the fill factor of the solar cell. Okay, so now we have recorded the readings. So let us come to the tabulation part and the calculation part to find out the efficiency and the fill factor of the solar cell. So this is the pre-recorded table for the voltage and current values at different load resistances, and we can see that the short circuit current that we got is 6.75 milliampere, and the open circuit voltage is 1.7 volt, and the power we can obtain by multiplying the voltage with the current. So here we should be careful about the units. So the voltage we have measured is in millivolt, the current is in milliampere, and when we multiply it, we have obtained the power in microwatt. Then we have divided it by 1000 to get it in milliwatt. So the next task is to plot the voltage versus the current graph. So here this is the IV characteristic of the solar cell for the recorded readings. So here we can see the short circuit current is 6.75 milliampere and the open circuit voltage is 1.7 volt. Together with this, we have plotted the power using the same voltage axis. And in the power plot, we can see that at this point, the power is maximum, that is 5 milliwatt, and the corresponding voltage and current are 1000 millivolt and 5 milliampere respectively. So they are denoted as VMP and IMP. So now, one more important thing that we have to notice here is that we are not joining these points one by one. Rather, we are joining it using a continuous curve, because we are having a limited number of data points and we need to cover the entire voltage range. So we should keep it in our mind that we are joining the points by using a continuous curve. So now let us plug in these values in the given formula and try to obtain the fill factor and the efficiency of the given solar cell. So here the fill factor, as we have defined it, is the ratio between the VMP IMP product and VOC ISC product, and we are getting it to be 43.5%. We have measured the area of the active solar cell. So the active area of the solar cell is 22.75 into 10 to the power minus 4 meter square, and the incident intensity at the given distance is 77 watt per meter square. So we can obtain the efficiency as the ratio between the output power to that of the input power. So it comes out to be 0.0285, that is 2.85%. So the final result for the current experiment is the fill factor is 43.5% and the efficiency is 2.85%. So at last we will be discussing few questions related to this particular experiment. So now let us have few questions which are related to the solar cell experiment, which are frequently asked by many students. So the first question is, what is the need of a PN junction for the photovoltaic effect that we observe in the solar cell? So the built-in electric field at the junction separates out the photo-generated electron-hole pairs. So therefore, the PN junction is essential for the effective separation of the electron-hole pairs. Simply, if you are having a p-type semiconductor or n-type semiconductor, the effective separation of the electron-hole pairs is not possible. So the next question is, what is the typical efficiency for the silicon-based solar cell? So the current efficiency under standard condition for the silicon based solar cell ranges from 22 to 26%, and the standard condition is called as the AM 1.5 radiation. Next question is, what is this AM 1.5 radiation? AM stands for air mass. So the AM 1.5 is the spectrum of standard sunlight, which is recommended by the Commission of the European Communities. It corresponds to a zenith angle of 48.2 degrees and a total irradiance of 1000 watt per meter square. Next question is, why most of the solar panels are blue in color? The blue color of the solar panel correspond to the polycrystalline silicon based solar cells. The blue color is mainly due to the anti-reflective coatings.